Alright, so this is a quick Chapter 9 review, just a real quick 5 minutes or so. So let's get started. Alright, so comparing liquids, solids, and gases, molecules are much closer together in liquids and solids. As you can see here, the solid molecules are close together, liquid molecules are close together, and the gas molecules are not very close together. Intermolecular forces play an important role in liquids and solids, but they don't play that big of a role in gases because they are so far apart from each other. Alright, liquid vapor equilibrium. This is when the rate of condensation is equal to the rate of vaporization, and the pressure exerted by the vapor over the liquid remains constant. So that's good to know. So long as both the liquid and vapor are present, the pressure exerted by the vapor is independent of the volume of the container. So if moles over volume stays constant, the moles over the volume stays constant the whole time. So P equals nRT over V does not change. That'll be helpful when you're calculating for any of these. Oops. Alright. You're also going to need to know this equation right here, which is natural logarithm of pressure 2 minus natural logarithm of pressure 1 equals heat of vaporization over R. R is right here, multiplied by 1 over temperature 1 minus 1 over temperature 2. And R and heat of vaporization must be the same units, so if if heat of vaporization is in joules, then R needs to be in joules, or if it's in kilojoules, then you need to convert this to kilojoules. Just multiply it by 1,000. And the boiling point, a liquid boils at a temperature at which its vapor pressure is equal to the pressure above its surface. So the lower the pressure, the lower the boiling point, and the higher the pressure, the higher the boiling point. Alright, this is another thing that I talked about in the chapter, phase diagrams. These are pretty simple, but we'll just go over them real quick. This is the triple point. This is where solids, liquids, and gas are all in equilibrium right here. This is the critical point up here. And basically how this whole thing works is, say we have a point right here where the pressure is 101 and the temperature is, say, negative 50 or something. It's below zero. And then we increase the temperature to 50. We would move over to here and the solid would melt into a liquid. And then what if we lowered the pressure down to 0.6? Then we would have the liquid turn into a gas. So that's pretty much how that works. It's not too difficult, but just go over it if you want to. Alright, intermolecular forces. Forces that act between molecules, they're stronger intermolecular forces means higher boiling points or higher melting points, but intermolecular forces are not as strong as covalent bonds. They are weaker than covalent bonds, which may be on the test, you never know. There are 3 kinds actually. This is the first one. It's dispersion forces, and that's when the electrons are in one place at a given time or any given moment. So it gives the molecule a slight positive or negative charge, and it happens, I believe, between all molecules. So dispersion forces become stronger when the molar mass increases, just because I believe it has more electrons. But this is a diagram on how that works. So right here, there are more electrons gathered in this part of the atom right here. And so this has a partial negative charge, and this side will have a partial positive charge. And this partial negative is attracted to this partial positive right here. The next one is dipole forces, and this is when an atom is more electronegative than the others, and it creates a partial charge in the molecule, so it becomes polar. Right here we have hydrogen and chlorine. Chlorine is electronegative, so that wants all the electrons near it, so it becomes partially negative, and hydrogen becomes partially positive. So they bond together. They have an attraction, and that's called a dipole force. And then this one's pretty similar. It's hydrogen bonds, which also need to be polar. But it's when hydrogen bonds with either a nitrogen, oxygen, or fluorine, and that is what forms a hydrogen bond. It has to be with one of these, and it's because there's a large difference in electronegativity between these three and hydrogen. So here's a little picture for you guys. Alright, next, network covalent ionic and metallic bonds. So network covalent solids are joined together by a continuous network of covalent bonds. The entire crystal is like one large molecule. You can see that right down here. Network covalent bonds, they're all just connected to each other with covalent bonds. It makes just one big thing right here. It's pretty cool. Next, we have ionic solids, which are held together by ionic bonds between oppositely charged atoms next to each other. You can see that right here. We have a cation and an anion, and they go together and they make this big picture of cations and anions. And then we have metals, which are composed of cations, which can be charged with +1, +2, or +3, and a bunch of electrons. And you can see that right here. You can see all the cations with the big pluses, and then you can see these little electrons that are around in there as well. It's also known as like a sea of electrons, is what some people call it. Alright, next we have the crystal structure. We have simple cubic, which is right here. We have face-centered cubic, which is right here. And we have body-centered cubic, which is right here. And so simple cubic is just 8 atoms whose centers are at the corners of the cell, and the atoms at the corners touch each other. So we'll just go back here to show you that. So because the center is at the corner of the cube, right here, only one radius of each of these atoms goes into this cube. So if you were to calculate the side of the cube, which is S, you would do 2 radius, because there are only 2 radii, I believe the plural version is. There are only 2 of them right there. And then there is face-centered, which is an atom at each of the corners, and there's an atom in the middle of each face of the cube. And the corner atoms don't actually touch each other, but they touch the atom in the middle of the face. And in order to calculate the side of that one, you use this equation right here, 4r equals s square root 2. And we'll just go and show you right here. That's this one right here. And that's because these corner atoms touch the middle one, but they don't touch each other. So you have to do some math to calculate the s for those ones. And then last we have body-centered, which the atoms are at the corners, and then there is one in the center of the cube. And the corner atoms do not actually touch each other, again, for this one, but they touch the center one. And to find the side of that cube, you're going to need to use this equation, which is 4r equals s square root of 3. And we'll just go back here and look at this. This one is body-centered cubic, and we got the 8 atoms in the corners, and then we have the 1 in the middle. So the corner ones can touch the middle one, which touches the diagonal one, but they do not touch the corner ones themselves. And I believe that is it. So I hope that helped you a little bit, but I would go read the chapter one more time. It has some valuable information that I couldn't get into this short little video. But I hope it somewhat helped you understand some of the concepts.